This is Joshua Kasirye, and I'm taking you through my assignment 2 for mechatronics design. And in this assignment, I'm required to produce a robot navigation model in MATLAB Simulink. And in this, the robot should be given a different set of coordinates and should travel and navigate to the desired destination. It involved different processes. In this, we started by developing the model of the robot. This is the model of the robot where it takes in the velocity of the left and right wheels and outputs x, y, and theta, where theta is the angular displacement of the robot in the x and y plane. And x and y are the coordinates in the x and y plane. Here is what we have as the robot plant model. And in this case, to get the velocities of the left and the right wheel, we are to provide them into the robot via the motors. Here we have the right and left DC motor models, and this is the DC motor model where it takes in velocity voltage and outputs velocity. And this is the motor driver, which converts the PWM cycle output from the PID controller into the motor driver, which converts it to voltage and then provide to the motor module. We have two motors, the one of the right wheel and the left wheel motors that provide this velocity into the robotic plant. At the same time, we have to control the velocity that the motor gives out. How? By getting this velocity and feeding it back into the PID velocity controller so it can control the exact velocity that is required to move the robot to the desired coordinates x and y and theta. We have two velocity controllers for both the left and right, the right and left DC motors. Now, to get the desired velocity, we have what we call the kinematic controller. Now, this controller is to help us control the motion of the robot in the x and y plane so that it can easily navigate to a desired path. Yes, and in this particular controller, it inputs the theta, which is being output by the model itself. It is fed back into the system, as well as the desired x velocity, or velocity in the x plane, and then velocity in the y plane, as well as the errors which are computed from the x and the y coordinates. These errors are gotten from the desired y and x, and then what we are returning as feedback from the system. Then the kinematic controller uses these to provide the suitable velocity and the angular velocity of the robot, which in turn we run through what we call a kinematic inverse model that converts these velocities of the linear velocity and the angular velocity of the robot into the angular velocities of the left and the right wheels. We convert them into linear velocities, which we feed into the earlier design controller to be provided by to provide an output of a PWM output to the motors, which in turn provide the velocity to move the robot. I hope this helps you understand the entire system. And when this is run, you can see that this is the desired coordinates. We want the robot to move from 0 across this path all the way to 0.5 on the x-axis. And this is the coordinate in terms of x and y, and we feed it into the controller. The controller computes the velocities into the velocity controller, and then the motors provide to us these velocities into the robotic plant. And then in the end, the robot plant also shows us our measured velocity and measured displacement in the x and y. And as you can see, the two graphs are really very similar, which shows that the robot was able to move from the initial coordinate to the desired coordinate following this particular path. This is the same path as the trajectory path as we earlier wanted the robot to follow. Yes, and in this case we use the DC motor as the actuator. As you can see, that this is the DC motor as the actuator. It's basically to help us convert the desired coordinates into velocity, and then that velocity is what we feed into the robot, and the robot to give us the desired coordinates. Also, I designed what we call the encoder, an encoder which is to provide feedback into the system in terms of velocities of the left and the right wheel. And this is an incremental linear encoder. It takes in omega, which is the angular velocity of the robots of one of the wheels, and it runs it through a sensor network, which is basically to convert the scalar value to electrical signals, which are to run through this incremental shaft encoder. And this incremental shaft encoder is to help us produce the A and B pulses. We call them incremental pulses, and these ticks are what we use to compute using the count up and count down models built in Simulink. Then they help us provide the encoder ticks. We get these encoder ticks and we divide them by the resolution of the encoder, which is 1984. In this case, it is the PPR, which is the pulse per revolution. We multiply again with the 2 pi circumference of the wheel to give us the desired distance. But if the initial distance is 0, we add it to 0. But if it is another value, we add it to it. So in this particular encoder design, we are putting in omega and we are receiving distance. So when it was run as well, you can see that as it is behaving linearly as expected, as the behavior of any linear incremental encoder. For every, since we are providing a constant omega, it shows that it is increasing at that steady speed to this desired distance. Then to understand or to implement the encoder into the system, we are picking the theta. In this case, theta is the angular displacement of the robot. We are feeding it into the inverse kinematic that helps us to compute the left and right wheels angular velocities from the theta of the robot. Let me just show you inside. So we have theta, we differentiate it to get omega, and then these omegas are multiplied with the gains, which in this case, for example, is the radius of the wheel and the radius of the robot as it turns, and then that is used to compute the omega of the left and the right wheels. That omega of the left and right wheels is fed into the encoder as earlier described for the both left and right encoders, which will give an output of again omega, but then in this case this omega is from the encoders, and then this omega from the encoders is then converted to linear velocity, which is fed into the system. And yes, for in this case we are not able to add it in yet, but the whole purpose is to get these velocities and feed them here as they feedback into the system so that the robot can work with the output of the encoder. This was also tested, and you can see that these are some of the velocities of both the left and the right wheels of the robot from the encoders, which is similar to what we expect as the behavior of the robot. Yes, thank you very much. Thank you.